Hello, welcome. It's the last lesson of the unit and last lesson of the year, so let's make it a quick, simple one, okay? Yeah? Let's do it. Okay. Real simple problem. No, question. Why are some cars fast and some cars slow? Hazel. Why are some cars fast and some cars slow? Uh, because some cars can go a greater distance in the same time. Yes, that's exactly correct. Very good. Good job, Hazel. Wait a second. Cars go different d over t. Their speed is a distance over time. Their velocity is a displacement over time. And yeah, some cars are faster, some cars are slower. Actually, not really. That's kind of circular logic. Of course, cars are faster and slower based on d over t because v is defined by definition as d over t. So that's fine, but not super relevant. Another question, Hazel. How do you define speed as a rate? I don't know. You help me out. How can we define speed as a rate? Use the word rate in your definition of speed. Most you probably, hopefully, said speed is the rate of motion. Speed is the rate of displacement. Speed is the rate of change of position. Those are all fine. It's not correct to say speed is the rate of change of velocity. That's acceleration, which is also a rate. Acceleration is the rate of change of velocity, so that's good. Rate means how, basically you divide by time, you look at it over a period of time, you compare the change in one thing over the change in time. If I get a raise of like $5 a year, then my salary is going up $5 every year. That's a raise. Anything that changes the same amount every time interval could be a rate if you express it per time interval. Okay. New question. No, same question, new answer. Daisy, why are some cars fast and some cars slow? The engine and their horsepower. Yeah, really good. Yeah, some cars have a really powerful engine, like a Bugatti Veyron, and some cars have a really bad engine, like a Ford Pinto. If you probably don't know what Ford Pintos are. They were a car back in the 70s, and the fuel was right in the back, and whenever another car hit them from behind, they would explode. Very famous, very bad car. But that's not really the case. Yeah, sure. A little like, I can't really draw Ford Pinto. Sure, a car, a little subcompact, like compact car, a little like commuter. A bad car might have a really weak engine with very low horsepower. If I had this like I don't know, like a Lamborghini Murcielago or something, it probably has a really powerful engine with a lot of horsepower. But so do other things. A big truck like a Bronco also has a lot of horsepower. It also has a very powerful engine. But they don't really go fast. Trucks aren't really known for their super high speed racing ability. So obviously a car with low horsepower can't go fast. A sports car with a high powerful engine can go fast, but trucks with powerful engines don't go fast. What do trucks with powerful engines do? Trucks with powerful engines are not built to go fast. They're built to haul a big trailer, to carry a whole truckload of logs. They're built to like carry a boat or like a mobile home or something. Another way to say they're built to do a lot of work. Yeah, a truck does a lot of work, carrying a lot of stuff, applying a big force, and giving something a large displacement. Does a sports car engine do work? What do you think? Yes, a sports car engine also does work. It applies a force on itself to give itself displacement, and thus give it a lot of work. Is a change of energy. For a sports car, it's mostly kinetic. W equals delta K. So a powerful engine can be used to go really fast or pull something really heavy. That's physics. Moving on. Why couldn't a Ford Pinto go 200 miles an hour? It's not what they look like. But even though the engine was bad, the engine was doing something, right? The engine is not really doing a lot of work, but it was applying some forward force. Wouldn't there be some forward acceleration? So imagine like the oldest, crappiest car you can imagine. Even why can't the worst possible car in the world eventually reach like 100 miles an hour or 150 miles an hour? Doesn't the engine apply some forward force? So won't it accelerate a little bit and eventually reach a high speed? Tell me, in real life, why every car can't eventually reach 200 miles an hour? This question separates ideal physics from real-world physics. In an ideal scenario, if the car has an overall forward net force, total force, it will accelerate. And if it accelerates for long enough, even a very small acceleration, we said earlier, is change in velocity over time, the rate of change of velocity. So it'll eventually reach a huge velocity of like 200 miles an hour, or meter per second, doesn't really matter, it's all hypothetical. It might take like a long time. That's ideal, hypothetical. In real life, that won't happen. There's air resistance, there's friction, there's wear and tear on the engine, the car will run out of fuel, hopefully not stored in the back of the car, hopefully somewhere like on the bottom where it's protected. In real life, a car can't accelerate forever. The faster it goes, the more energy is needed to make it go even faster. So you do need a powerful engine. Ideally, a car moving forward doesn't require energy to keep going, doesn't require work to keep going. We'll keep going no matter what. And if it accelerates, it'll go faster and faster no matter what. But in real life, if you have like some kind of fancy sports car and it's going really fast, like 100 miles an hour, you need a lot of power to keep going faster, to keep it going at that speed, and to keep it accelerating even more. The engine must apply a large force to keep up a large velocity. It also needs to give the car a lot of energy, it also needs to do a lot of work. So that was pretty nice. Yeah. Maybe I'm just making up numbers, which I normally do anyway. Let's say this car weighs 2,000 kilograms and it wants to go up to 50 meters per second. How much energy would it take? Now this. K equals 1/2 mv squared, 1,000 times 50 squared, 25, 5 zeros. This many joules. I might have made a mistake, but it doesn't matter. Let's say the little engine in the Ford Pinto, it's doing its best, it's trying, it's like 50 years old, but hey, it has gas. Couldn't it eventually do this much work? Yeah, that's a lot of work for an engine to do, but the engine could do that work, in theory. But the car still won't reach the same speed as this Lamborghini Murcielago. Because it'll take so long, so much time for this little Ford Pinto engine to do this much work that air resistance and friction and other problems will slow the car down and it won't reach the speed. So a powerful engine can do this work on the fast car much faster. What was the point of this whole discussion? We talked about how acceleration is the rate of change of velocity. Velocity is the rate of displacement. The rate of work in a certain time is called the power of a car or a person or anything. Yeah, that's it. If I'm lifting rocks and doing work on the rocks, the work I do, divided by the time it takes me to do that work, is my power. They use some weird words in physics for power. They might say the power used, and that would be fine, but they'll often say the power exerted or the power developed, like you develop film, except you don't because no one does that anymore. Just it doesn't really matter what word they use, it's power. Power is work per time. The work someone does in a certain amount of time is the power that they can create, generate, develop. No matter what kind of power. No matter what kind of work. No matter what kind of energy is generated. There's a nice thing here. If you know that ideally to keep a Bugatti Veyron going 15 meters per second in a frictionless, ideal physics dream would take no force. But in real life, it does take force. In real life, because of air resistance and friction, you need force to keep Bugatti going a very fast speed. You need a force. Ideally, acceleration is force over mass. So force will cause acceleration. But in real life, to keep a constant speed, v, you still need to apply force, F. And a very nice result comes out of this. How much work are you doing, or is the engine doing, to apply force F and keep the car moving speed V? Well, work is F times D. Times cosine theta, assume that's 0 degrees, theta equals 1, cosine equals 1. Well, if work over time is Fd over T, the power developed by this car's engine to keep it going speed v with force F is Fv. P equals W over T, or P equals Fv. Both are okay, no issues there. Hooray, physics. I think that's all I want to talk about today. Hopefully we're all going to have a great break real soon. That's it. Last question. Who did I ask? Sage or Sage? Sage. Watt is unit of power. Yes, that's right. The unit of power is a watt. W-A-T-T, capital W. It's the same symbol as work. Very confusing, but very true. If I can do 51 joules of work in 3 seconds, the power is the work over time. This W is work. 51 joules over 3 seconds is 17 watts. This W is work. This W has a number in front of it, so it's 17 watts. Sorry, can't really change it. Not my fault. And if it's joules per second, and joules are kilogram meters squared per second squared, and a watt is a kilogram meter squared per second cubed.